what can we learn from Antarctica's past that can help us understand events happening today and in the future? Hello, friends. Jim here. Drilling into Antarctica's past. The West Antarctic ice sheet melted rapidly about 8,000 years ago. Could that event foretell the future? And here's a photo showing bubbles trapped in 8,000-year-old ice from the West Antarctic ice sheet hint at a previous period of sea level rise. Right? You get these gases here. You can find out what gases are present in those bubbles and the isotopes. And using the isotopes, you can reconstruct what happened in the past. The ice sheets covering Antarctica contain enough water to raise sea levels by 57 meters. That's enough to cause flooding in low-lying coastal communities globally. A recent study published in Nature Geoscience showed that the West Antarctic ice sheet went through a period of rapid melting around 8,000 years ago, and questioned whether this turn of events in the past could be a sign of what's to come in the future. The melting of the West Antarctic ice sheet would raise the sea level by about 5 meters. That's just the West Antarctic ice sheet, said Eric Wolf, a co-author and climatologist at the University of Cambridge. And it sits on bedrock that is below sea level, making it particularly vulnerable to a warming ocean. As sea levels rise, water could seep underneath that ice sheet and unground it. Research indicates probably happened before. So, how do you figure this stuff out? Well, you drill ice cores. Right? You drill in there and you get ice cores. And the ice cores, the snow falls, pockets of air gets trapped by subsequent snowfall, preserving the atmosphere from when they were buried in nearly pristine condition. And then as the snow accumulates, it compacts, turns into ice, and so forth. Using ice cores, we can literally analyze the atmosphere from the past, said Isabel Rowell, a postdoc researcher at the BAS, British Antarctic Survey, also a co-author. And here you see, here's an ice core. Nice miter saw. And the ice core, you can age it, and you make a slice there, and you make a thin slice, and you analyze it. In 2019, scientists and engineers spent 45 days drilling 651 ice cores at the SkyTrain ice rise, a large mound of ice on the edge of the Rhone ice shelf, a section of the West Antarctic ice sheet that floats in the Weddell Sea. SkyTrain itself sits on a dome of bedrock that rises above the rest of the seabed. Its ice has never been overridden by ice from somewhere else, so the cores collected could reveal a detailed climate history at that location. So, researchers wanted to measure how SkyTrain's elevations change over time. They did this by assessing the pressure, isotopes, sodium trapped in bubbles at different layers in the ice. The air pressure of bubbles trapped in the cores is a good proxy for both temperature and elevation. Lower pressure can often indicate lower temperatures and higher elevations. Basically, think of a thinner air on a mountaintop and an icy mountaintop. They can also measure water isotopes as proxies for past temperatures. Isotopes indicate the temperature at the time the snow fell. And in ice dating 8,000 years ago, researchers found an anomaly. There was what looked like almost a discontinuity in the water isotopes, where the temperature rapidly increased by several degrees over a couple of hundred years. There was no significant rise in temperature across other parts of Antarctica at the time. So the researchers inferred that the isotope and temperature jumps of SkyTrain were connected to a loss in its elevation, implying a loss of ice. Finally, researchers noted the sodium content of the ice cores. Sodium could come from either the open ocean or the sea ice surface, both of which are salty. This is basically referring to sea spray, oceanic sea spray, right? Seawater is salty, hence the sodium. A change in sodium content tells us as a first order effect that the ocean got closer. In this case, higher sodium concentration says that the ice shelf edge retreated so that SkyTrain was closer to the sea. Interesting. Under the pressure isotope and sodium data, researchers surmise that toward the end of the last ice age, warmer ocean water must have flowed underneath the West Antarctic ice sheet. Part of the ice sheet detached from the bedrock below and floated, forming what is now the Rhone ice shelf. And we know the Rhone ice shelf is threatened. I've done some videos on that. The area where SkyTrain is located was no longer restrained by grounded ice, which caused the ice to shrink. Within just 200 years, the ice at SkyTrain thinned by, and this is a holy cow moment, 450 meters. 450 meters. About the height of the Empire State Building. Once you unground the ice, it's really going to retreat very fast. Ice sheet models predict that the West Antarctic ice sheet could melt in the next few centuries. But as expected, is uncertainty about when, where, how quickly this will take place. Ice cores such as those from the study can help make predictions, help make projections, help increase the accuracy of said predictions and projections by offering insight into how the ice sheet behaved during previous periods of warming. The new work provides really strong evidence of past changes in an important part of the ice sheet, involving processes that are likely to be important in the future, said Richard Alley, a geologist at Penn State U. We have known for a while that the Antarctic ice advanced during the Ice Age, often to near the edge of the continental shelf, and that as the Ice Age ended, the warming ocean and rising sea level forced a major retreat. That research offers a wonderful target for model testing and improvement. Understanding the parameters of how ice melted in Antarctica in the past, Rawls said, may help give some context as to what it might do in the future and what that might mean for sea level rise. That ice has to go somewhere. It's going to the ocean. It's melting, causing a rise in sea level. We're not saying the exact same thing is going to happen, but it helps us understand the mechanisms of how things have changed in the past. But yeah, it gives us a good idea what's likely to come. Once again, another demonstration how if you want to get an idea, a handle what's happening now, likely to happen in the future, look to the past. That's exactly this research does. And we can again thank Wally Broker for pioneering the techniques used. He introduced isotopic fractionation to recreate past climate. Even though he's no longer with us, his influence is still widely felt. And we know that the oceans are warming. I've done videos explaining how the warming ocean is getting underneath the ice sheet, the cantilevered land ice, and melting it from below. Well, whether it's Thwaites, Pine Island, West Antarctic ice sheet, Rhone ice shelf, they're all under threat. And you melt it from below, and as I say here, you unground the ice, you free it. And if that bedrock is below sea level, well, it lubricates the entire thing. So then you can snap off that ice and it gets out into the ocean. You can then accelerate the melt, what of the ice that's on the land. That could start accelerating out. And so when they refer to, as stated here, water would seep underneath the ice sheet on ground, causing it to retreat. The ice is retreating, back away from the ocean because it's breaking off. And then this allows the ocean to get closer to whatever land ice remains and can further impact how it behaves. But when you break off that ice that's on the grounded line, that just helps the land ice behind just basically gallop towards the ocean, and there where it gets subjected to the same treatment. Warm ocean water ungrounds it, breaks off, etc. So this is very interesting findings here, and a good way to model what's likely to happen in the coming decades and possibly centuries. So there you have it. Thank you for your time.